Our next speaker is Sandra Pott. She's going to talk about multiplying H1 and BMO dyadically. Sandra, please.
Okay, thank you very much. And thank you very much to the organizers for inviting me. It's a great pleasure to be here, and especially after Daniel Girela's nice talk about BMO. So this is just perfect. I should say that what I'm talking about is joint work with Odysseas Barkas, Salvador Rodriguez, and Alan Solar. And there are different bits. So there are parts is from a collaboration just with Odysseas, and part is from a joint paper with the four of us. So I'll maybe indicate it at some point. So I want to talk about multiplying H1 and BMO. And so the story started with a work by Bonamy and collaborators in 2007. And they proved the following. And at the first moment, one wonders, what is there to prove? So the starting point was the following. And this is sort of the first in a series of works. And I think the first, these are the authors of the first paper, but there were following papers. So these were Bonamy, Ivanic, Jones, and Zinsmeister. And they observed the following. There exist bounded bilinear forms we have one form which goes from BMO times H1, and here I should explain by BMO I mean always the real BMO, but thought of in the unit circle, and you can think about it as the real parts of the analytic BMO spaces, which Daniel has just talked about, and the same with H1. So BMO times H1 of T to L1. And there is another bilinear form, which goes from BMO on the circle times H1 of the circle to another space, which is called L-log. Sorry, I should say H-log. Such that the sum of these two bilinear forms is just the ordinary product. I apologize for the noise. It's the rain in Sweden, and which is coming on the roof. So that means if you have an H1 function and a BMO function, and you multiply them with each other, then you don't ever end up with in L1. There's a certain part of the product which does end up in L1. That's sort of this, which is denoted by the bilinear form T. But there's also a part which doesn't land in L1, but in a slightly larger space. And I'll just explain what this larger space is. So here we will need the Orlic space L-log, and that's just, here we take the infimum over all mu's with the property that the integral over phi of 1 over mu of modulus f of t dt is less or equal to 1. And here the function phi, which we use here, is modulus t divided by log e plus modulus t. Okay, so what that means is we replace L1 by an Orlich space. If this function phi, which I've taken for the definition of my Orlich space here, if this was only the numerator, only the modulus t, then we would just have L1. But the phi of t is a little bit smaller because I have a log of e plus f of t in the denominator. So it's a space which is slightly bigger than L1. That's the log space, the Orlich space belonging to this function phi. And H log just means that I have a function which is in H log if it's maximal function, or maybe you could also take the Hilbert transform or the conjugate function as Daniel did yesterday in his definition of H1. So if mg is in M. So you end up in this space which is slightly bigger. And so what I want to talk about today is first, why is that so? Is there an easy way to think about it? And can this maybe be extended to other settings? And yeah, I'm particularly interested in the multiparameter setting. And in the end, is this H log space nice? Okay, and I'll just open a new page, a moment. So the first question is, why is the product B times F not in L1 if B is in BMO and F is in H1? It's kind of counterintuitive because we are, when we think of LP, LQ duality, or even the HP, HQ duality, which Daniel talked about yesterday, then if you take a function and a function in the dual, the product is in L1. But what happens if you go to the endpoint and you look at the BMO H1 duality, also which Daniel talked about today? There is a property of the space H1, which kind of spoils what you're trying to do. And that is the following. Well, if B is in BMO and F is in H1, then the product, this integral of the product, exists in some way. However, this thing is not integrable in general. Because if you can observe that if B is in BMO, yes, then the modulus of B will also be in BMO. But if F is in H1, then in general, the modulus of F, sorry, is not in H1. Because if you look at the real H1, cancellation properties are very important. And if you take the modulus of f, you lose these cancellation properties, and the functions you're looking at are no longer in H1. So you cannot just think of the integral of the product of these two. The modulus of b will be okay, but the modulus of f. So that's the first remark about what's going wrong here. But I find it quite interesting to think of this in a dyadic way, that there the problem becomes more transparent. And I should also say, Daniel was mentioning bad multiplier properties of BMO, so that if you start multiplying there, bad things happen. And I try to illustrate that a little bit. So we try to multiply dyadically. So for that, we take dyadic versions of the spaces BMO and H1. So space BMO of D, this just means you take exactly the same oscillation property as the one which Daniel introduced yesterday in the course, but you just take it on dyadic intervals, or because we are really on the circuits, dyadic arcs. So arcs which you get by subdividing the original circle first into halves, then into the quarters, and so on. So, and here we would take the B's, let's say those in L2, with the property that the supremum, and here I take only these dyadic intervals, not all intervals. Where this supremum is finite. And there's also then as the dual, a dyadic version of H1. And if you remember the definition of the real H1 space, which we had yesterday, these were just functions in L1, such that the conjugate function is also in L1. The conjugate function is also the Hilbert transform. And here in the dyadic setting, instead of taking the conjugate function, we take the dyadic square function. And I'll just write this down. Dyadic square function is the following. We take the high expansion of f, the formal high expansion, and this gives us high coefficients. These are these fi's. And I use this to make the square function, the dyadic square function. So this is the dyadic square function of f. And this should also be in L1. So everything is analog to the continuous theory, only I have this dyadic square function instead of the conjugate function. Okay, so I'm just taking a new page. So what happens if I multiply dyadically here? So, well, I'm really only multiplying. So I write both f and B with their formal H expansion. And if I now take the product, then, and I just multiply term-wise, then I'll get a non-trivial contribution only if the intervals I and j have a non-trivial intersection. And now the nice thing about dyadic intervals is if they have a non-trivial intersection, then one has to be contained in the other. So if you have an I and a j, say I and here a j, you can have a picture like this, but you cannot have a picture like this, that they are kind of intersecting without one being contained in the other. This cannot happen with dyadic intervals. So this makes the combinatorics of multiplying things very easy. And so that means I can get only three kinds of terms. Either I and j are the same when I multiply. In this case, I'll have a square of a half function, and that's just a characteristic function divided by I. Or I have the situation that I is strictly contained in J. Okay, this one. Or the other way around. I contains J strictly. Now, if I write this a little bit differently, then sorry here, that meant only all the I's. So if I is strictly contained in J, then the half function Hj, then it will be either in the left or in the right or in the right half, and the half function Hj is constant there. So what I pick up here is just the average of f over j. And then for the last term, it's exactly the other way around. Then I will get an hi, and I will get, I'm sorry, here, this is an I. Here, there will be an average of B. And there are coefficients Fi. They are well known and well studied in harmonic analysis. These are paraproducts. This is the paraproduct, which is often called pi b. This here is sometimes called delta b f. And this here is a term which is sometimes called rb. And if we look at the last term first, you see something which should scare you very much. Namely, it is an average of a BMO function. And averages of a BMO function, they behave badly, although not too badly. And well, how badly that we saw yesterday. So we have seen that a BMO function is in general not bounded. It can be an unbounded function, like for example, a logarithm, but also it cannot be very much worse than a logarithm. And here, that's expressed in estimates that such an average as of a BMO function can be estimated by the logarithm of the length of I. And that's actually exactly a consequence of the John-Nirenberg theorem, which was introduced yesterday. So the John-Nirenberg theorem says that a BMO function can be large only on an exponentially small set. Yeah. So if you look at, say, if you have a BMO function B, and you look where this BMO function is greater than a lambda, some lambda, then this is less or equal than e to the minus, and there will be some alpha times lambda. That inequality we saw yesterday. And if you just integrate over level sets, what you'll get is if you average over an interval of length I, then you can estimate with a log of I. Now, if you look at this last term, how this MIB appears there, it's as a H multiply. That means you have a function which has a H, for which you have a H expansion, and each H term you multiply with some constant. And this constant is the MIB. And this can be unbounded in general for a BMO function. So this here is an operator which doesn't map boundedly from H1 to H1 or even to L1. The other two terms are fine. This here will end up in L1. And this here will even end up in the dyadic H1. So one can show this. So the last term is the one which gives us the trouble, and which means that we don't end up in L1. Okay, but how do we get into the H log? That is the next question. Just open a new page. So here's a lemma, which is a key lemma in this work of Bonamy and collaborators. But here's a proof which shows that this is just about John-Nirenberg theorem. So what the lemma says is, if we forget about Hardy spaces and we just take a B in BMO and an F in L1, then the product B times F is in L log. So not in H log, but in L log. And that means we haven't taken any maximal function or square function. We just look at the function B times F directly. And the proof is quite easy. I'll just show you that because I want to use this in a more general setting later. So we can assume without loss that the modulus of F and B are both greater or equal to 1. Because wherever either of the two is bounded, I have an easy L1 estimate. And now let's just at the ANs. Let that be the point where f of t has approximately modulus 2 to the n. And now let's look at this funny integral, which we have for the log norm. So we have a e times f of t. And here we have a logarithm of e plus b times f of t. T. Okay, so I just split it up into these disjoint sets an. Then in the denominator, I have inside the log, I have something which is at least 2 to the n. So the log gives me a 1 over n. So I should not really. And then I have an integral over an. And here I've already said here on the an, the f is approximately 2 to the n. Put that in here. Okay, and so I was mentioning before, we'll just go back here, that the average of the average of a BMO function over the interval I can be controlled by log the length of I, and that this is a consequence of the John-Nirenberg theorem. So you can apply this John-Nirenberg theorem not only to intervals, but just for general open sets. And what you'll get there is the same log, which turns up. So let's go back here. Yeah. So this here, again, by the John-Nirenberg theorem, this is less or equal than the log of the size of an times the size of an times the BMO norm. Okay, and once you're there, then you have solved the problem, because with the an, we could have two situations. Well, I know the an cannot be bigger than a 2 to the minus n. Yeah, just because we had an L1 function we started with, say it has L1 norm 1, and then it cannot be bigger than 2 to the n on a very large set. But let's just say, let's take the n's where a to the n is, say, greater or equal than 2 to the minus n half. What would happen then here? In that case, this here would still be approximately approximately n. And this here, well, it would just be the size of an. So what would happen is that this term would cancel against this one, and we would get a sum over all 2 to the n an. And that is fine, because the an's were just the level sets of the f. So what's written here is just the L1 norm of f. So that case is fine. Another case then, but we might have other n's. So we also have to consider the ANs, which might be smaller. In that case, we have a slightly different estimate. So we have a sum over all n's. Here, we have a 2 to the n over n. And then say we set half, here we would have, we might end up with an n half. And this would be 2 to the minus, I'm sorry, I shouldn't have minus n half, it should be a 2n here. N here in both. 2 to the minus 2n. And then you see this is also fine. Yeah, because you have a 2 to the n and a 2 to the minus 2n. So that's also fine. So both cases are fine. And the whole thing is just a consequence of the John-Nirenberg theorem. Okay, so this is about the kind of the easy multiplication in the one variable dyadic case. And if I now want to end up in H1, in H log, not in L log, what can I do? So I had my RDF here, which was the bad term from the product. And I wanted an H log, not only an L log. So what I have to do is I have to take the square function of the RBF and take the L log norm of that. So let's write down this dyadic square function. So the H terms of the RBF, remember the RB was just a H multiplier. The H coefficients Fi are being multiplied with MIBs. So I have an MIB here, squared, Fi squared, and the whole thing is square. So of this, I want to take an L log norm. And now, if I fix a T and I look at the sum, then I'm interested in all the i's which contain the T. So that the chi I, that I will have a non-trivial term here. So I'll have a supremum over all the dyadic intervals which contain the T. And then I will take a supremum of all the MI's turning up here. So for each T, I've pulled out the supremum here of the MIBs. It's still the L log. But the F was a dyadic H1 function. That means the dyadic square function is in L1. And this here is the maximal function of a BMO function. This is not itself in BMO, but the John-Nirenberg theorem, or the form of the John-Nirenberg theorem, which I showed you, also holds for MB, the maximal, sorry, the direct maximal function of B. It can only be big on exponentially small sets. So exactly the same proof, which I just showed you for the lemma, is working here as well. And that means that this here is also less or equal than the BMO norm of B. Times the H1. So in the dyadic settings, these proofs become very simple. Are there any questions? Because I wonder, I hear nothing, so I wonder whether there's still a connection to the Fields Institute.
We hear you now.
Yeah, okay. Okay, so what which means that this connection is now very easy, and you can very easily move from the one setting to the other. So I don't want to give any details now, but if you understand the dyadic setting, you are in good shape. You can do other things. And the other thing we were interested in was what happens in the multiparameter setting. So if you take BMO in several parameters, and for that I first have to explain a little bit how the BMO then looks like. Well, really, I will only be talking about two parameters. And H1 also. And there's a whole class of BMO spaces, and I believe we'll hear more about that today from Komla, who's talking about multiparameter matrix weights, that there's, for example, a space little BMO. And what you do there is, say, you have a function in two parameters, and you just say, for each t, b of this, whenever you freeze one variable, the resulting and you take a uniform bound of all these BMO functions which you get. That's the little BMO, and that, for example, appears naturally when you study Journet operators, or if you study weights in several parameters. And if you look at such, this little BMO also has a dual, which is a sum of like an L1 of H1 space. You can write this down and you can multiply things, and you can basically use this one parameter tricks, and it will be fine. And you can write down things, and you do more or less the same as you did before, only parameter wise. That's not so bad. But there's another BMO space, which is natural if you look at the H1, the complex H1 in two parameters. So you can look. So this was the little BMO. There's another one which is called the product BMO, and that is the one which is more natural from complex analysis point of view. So you can have an H1 complex H1 space of on the bi disk and the corresponding real H1 space on the bi circle, and then you can ask for the dual of that. And this is characterized by a more complicated oscillation condition. So, and for that, it's maybe useful to go back for one moment to the oscillation condition just over intervals. Say we have a dyadic interval. Look at the oscillation condition. Which Daniel introduced yesterday. So here's a B. So if you now look at the high expansion of B, then the average of B catches all the contributions of the hard terms from intervals which strictly contain the I. And the B minus the average, these are the remaining terms. These are the contributions of all the hard terms which are strictly contained in I. So you could also write it like this. No, I should say not strictly contained in I, but contained in I. So you have, you can understand the ordinary BMO norm like this. And if you are out, and this is the one where you take an arbitrary open set omega, you look at all the rectangles, dyadic rectangles, that's a product of two dyadic intervals. So, and you look at the L2 norm of this thing, and then you divide by the size of this open set omega. And you want that all these oscillations over arbitrary open sets, that they are uniformly bounded. And now there is, there is also a Jahn-Nirenberg theorem which goes with this. This now says if you take the B of ST, which are greater than lambda, but it looks a bit different because here you won't have a lambda, you will have a square root of lambda. And if you, so, oops. If you now try to integrate such a B from product BMO, so of an open set omega, then the fact that you don't have a lambda but a square root of lambda, this gives you that you have, instead of the log of the size of omega, you get a square on this. And if you now go and try to imitate the proofs, which you do in one parameter, then this log square is your enemy because it always comes in your way. You sometimes want to, you can compensate for a log, but you cannot compensate for a log square. So even if you try to investigate LMO in two parameters, or the multiplier algebra of BMO in two parameters, this log square comes in your way. So the solution is that you have to keep in mind the independence of both parameters. And so the time is nearly up. So I will just state FD in BMO product. And I'm sorry here, this was meant to be B. And F in L1, just in an ordinary L1. Then F times B is in, now this is written a bit cryptically. So what I mean here, what we have to do is, sorry, I should write the sum here. So what I mean here is that if you remember, we had this function phi of t, which was modulus of t divided by log e. That was the function defining our Orlick space. So what we have to do is we take I'm sorry. We take an f of st, then we take an L log norm, and let's take it relative to t. The resulting thing is a function in S. And of this function in S, you then take an L log norm relative to S. And here it matters the choice of S and T. It's not immediately symmetric as it would be in LP. And then you switch around the role, the S and the T, and that is this other space. And you can prove that, I should say this is quite easy. That you then end up in this sum of spaces. What we really wanted to do is we wanted to have the analog of this bad part of the product. And we wanted to see that we can even do something with the square function. And you see, I've seen in the one variable case, it's very easy to go to the square function. You just plug down you just immediately get a product of maximal function and the square function, and you immediately use the lemma. This is not so clear in this case, because in this case you have the strong maximal function, and it behaves not as well as the maximal function in one parameter. So we don't know yet whether we can go from this, how to go from this L1 result, L log result to the H log result. But at least we understand these products. Okay, and just for 1 minute before I finish, I want to persuade you that H log is a nice space, and this is by means of a Hardy inequality. So here we go back just to the one parameter setting. And this is this theorem, and this is by Barkas, Rodriguez, Solar, Pott. There's also and this here. And this says the following. So let F be in H log, now back in one variable. Then the sum over all n from minus infinity to infinity, n unequal to 0, f hat of n divided by n times log n, maybe log n x1, is controlled by the H log rule. And this is shown. So you get an analog of the classical Hardy inequality, only you have one extra log term which you need. And sharpness here means if you try to do this with a smaller power of log, then it doesn't. Okay, that's everything I wanted to say. Thank you very much for your attention.
Thank you indeed. Let's thank Sandra. Is there any question or comment for Sandra? Sandra, if there is any reference, you can mention it or share it with us too for your work.
Okay, so this is a new paper which is to appear in Archiv für Mathematik, but I don't know whether it will appear still this year.
Archiv der Mathematik, okay.
And the other one, the two parameter result is not published yet. So this one.
Okay. Thank you very much. Let's thank Sandra again.